Okay, so today we're going to move on to section 9.2 on countably infinite sets, but we didn't quite finish up 9.1 last time. So the last thing that we talked about was the pigeonhole principle, which says that if you have finite sets A and B, and the cardinality of A is greater than the cardinality of B, so you have a bigger set and a smaller set, then any function from the bigger set to the smaller set cannot be an injection, basically because there's not enough room inside of B. Okay, so you could also ask about a surjective analog. So let me write down a theorem, which you will provide in your homework, which is the following. If A and B are finite sets, and the cardinality of A is less than the cardinality of B, then what do you think you could say about any function from A to B? Right, so here A is smaller than B in the sense of cardinality. So since we're talking about finite sets here, A has fewer elements than B. And so hopefully you can guess that any map from A to B cannot be a surjection because you don't have enough elements in A to actually hit everything in B. Okay, so you'll prove something like this on your problem set. You'll prove, I guess, the contrapositive because that's how I have it stated in the notes. So if A and B are finite sets, and F from A to B is a surjection. So if I'm just writing down the contrapositive, then the cardinality of A is greater than or equal to the cardinality of B. Okay, so the thing in blue is just the contrapositive of the thing in black. Okay, another thing that we proved last time is if A is, again, here, A and S are finite sets, then if A is a subset of S, then the cardinality of A is less than or equal to the cardinality of S. So this is saying that as long as the set is contained within another set, then the cardinality can't be any bigger. But actually, we would like to say something stronger. We would sort of like to say that the only way for them to have the same cardinality would be if they were the same set. Right? So we would like to say that actually, if these two match in cardinality, that would imply that they're actually the same set. In other words, if you were actually a proper subset, then your cardinality would actually have to go down. So we can in fact prove this. Let me say it like this. If S is a finite set, then it is not equinumerous with any of its proper subsets. Okay, so again, what we know is we know that if A is a subset of S, then cardinality of A is less than or equal to cardinality of S. What this one says is that if A is a proper subset of S, then the cardinality of A is actually strictly less than the cardinality of S because they're not equal. Right, so I mean, I guess really what this is saying is that it's not equal. But since we know that it's less than or equal to, that means it's strictly less than. Okay, so this is getting like sort of a more precise handle on cardinalities of subsets. Okay, and this one we can prove. So let's suppose that A is a proper subset of S. So again, the way to write this is like this. Right? A is a subset of S, but it's not equal to it. So we want to show that the cardinality of A is not equal to the cardinality of S. But now, since A is not a proper subset of S, I mean, since A is a subset, but not equal, since it's a proper subset, what does that mean? This means that there exists some X in S such that X is not in A. That's how you can fail to be equal, right? If you're this is what it means to be a proper subset. There's something in S that's not in A. But now we have a lemma. By a lemma from last time, which we didn't prove actually. But the cardinality of S, if you take away this element, is equal to the cardinality of S minus 1. If you take away a single element in S, the cardinality goes down by 1. Right, and we know that A is actually a subset of S minus X, because every element in A is in S. And if you take away X from S, well, X is not in A. So it's still true that every element in A is in this slightly smaller set. Hence, by this theorem, let me just underline it in blue. By this theorem, the cardinality of A is less than or equal to the cardinality of S minus X. Right, but the cardinality of S minus X is equal to the cardinality of S minus 1, which is less than the cardinality of S, because a number minus 1 is strictly less than the number. So this shows that these two numbers are not equal because one is less than the other. Okay, so this says that for finite sets, we have a really good handle on equinumerousness. If you take proper subsets, the cardinality sort of always goes down by 1 as you take elements out, right? So the only proper subset that a finite set is equinumerous with, the only subset that a finite set is equinumerous with is itself. Okay, let me just make a note that this is not true for infinite sets. So this theorem is not true if you remove the finite hypothesis. Right, because like the naturals are a proper subset of the integers, but they are equinumerous. Okay, so finite here really does matter. Okay, so this takes us into section 2, which is actually called infinite sets. I don't know why I wrote countably here, but we're first going to talk about countably infinite sets. Okay, so let me first say that actually this theorem gives us our first theorem about infinite sets if I take the contrapositive of this theorem, right? So this theorem says if S is finite, then it's not equinumerous with any of its proper subsets. So the contrapositive would be if S is equinumerous with any of its proper subsets, then S is infinite. So this is actually our first theorem about infinite sets. If S is equinumerous with one of its proper subsets, then S is infinite. Right, which is kind of nice because at the moment we don't really have a nice way to show that a set is infinite. Let's go all the way back to the definition. It's not that far back actually. It's somewhere here. Right. To be finite means that you're empty or you have a bijection to the first k natural numbers for some k. To be infinite, all it means is that it's a non-empty set that you can never write in bijection with any first k natural numbers. So like this definition is not a very constructive definition, because in order to show that something's infinite, you have to show that there's no possible way to write down any bijection to the first k natural numbers for any k. That's kind of difficult, I think, because you have to prove kind of a lot. So since this is our definition of infinite, it's kind of hard to show that any particular set is infinite. How can I show that the integers or the reals are never in bijection with any n sub k? It's not that obvious. But this corollary gives us a nice way to show that a set is infinite. So we actually already have a series of examples. So we saw that n was equinumerous with z. So this will mean that z is infinite. Okay, also, we will show in 1 second, our next theorem will be that if a and b are equinumerous and a is infinite, then b is infinite. So once we know that z is infinite, and we know that n is equinumerous with z, the next thing we'll prove is that this will mean that n is infinite. Okay, we saw that the interval from 0 to 1 and the interval from 0 to 2 inside of the reals were equinumerous. So this means that 0, 2 is infinite. And again, by the thing that we're going to show next, this means that 0, 1 is infinite. So there are infinitely many real numbers between 0 and 1. This is actually the first time we have a rigorous way to show that. Okay, so this is a nice, useful way because it's sort of immediate. Of course, it's not the only way to show that a set is infinite. It's just the first way we have. In fact, like the next theorem, by next, I mean it will be proved on your problem set, but I'll state it right now. So this is to be proved on problem set, which is let A and B be sets. 1, if A is equinumerous with B and A is infinite, then B is infinite. Okay, so an infinite set is never equinumerous with a finite set. 2, if A is a subset of B and A is infinite, so this is like B contains an infinite set as a subset, then sort of B has to be big enough to be infinite. So then B is infinite. Okay, so these are sort of very natural. Well, hopefully these things are very natural, right? To be equinumerous sort of means you have the same size. So if you're equinumerous with something infinite, you must be infinite yourself. And then somehow having subsets means that if you contain another set, it means that you're at least as big as that set. So if you contain an infinite set, you must be an infinite set. So hopefully these sort of make sense, but let me just say that as an example, we already know that n is a subset of z, is a subset of q, is a subset of r, is a subset of c even. And so now that we know that n is infinite, this will imply that all of these are infinite. I mean, we know that z is infinite too. Okay, so now I want to talk about countably infinite sets. Okay, and the point is that the very first natural infinite set is definitely the natural numbers. Right? So the first infinite set that arises naturally, even like as a child, right? Is n. Right? When you're a little kid, you're like, oh, I'm gonna say like a huge number, and then your sibling is like, oh, I can name a bigger number, just take that number plus 1. This is really some sort of comment about the infinitude of the natural numbers. So now we should ask about what can we understand about the cardinality of this very first infinite set. We know that it's infinite, but can we say anything more about its cardinality? Can I put it in bijection with the integers? The answer was yes, we already saw that. Can I put it in bijection with the interval from 0 to 1? Can I put it in bijection with q? Right, so lots of questions. So we want to understand its cardinality. Right, like is n is equinumerous with z, we know this, but is n equinumerous with the interval from 0 to 1? Or is n equinumerous with the rationals? Or is n equinumerous with r? Are any of these equinumerous with one another? So the first definition I'll have is we have a special name for the cardinality of the natural numbers. So the cardinality of n is denoted by Aleph sub 0. Okay, so this is the Hebrew letter. Aleph, it's the first letter in the Hebrew alphabet, if I'm not mistaken. So you read this symbol as Aleph naught or Aleph 0, and I'm pretty sure you tech it as \Aleph. So this is like the first infinite cardinality we should understand. Aleph naught, the cardinality of the naturals. Okay, we say that a set A is countably infinite if A is equinumerous with n. Right, so we will write that the cardinality of A is equal to Aleph naught. So a countably infinite set is one that's the same size as the natural numbers. It has cardinality Aleph naught. We say that a set is countable if it is either finite or countably infinite. Okay, an infinite set that is not countable is called uncountable. Okay, so let me just make some comments here. The intuition behind this notation of, this definition of countable is like a countable set is literally one that you can count. Right, so why is this called countable? So the point is that if you have a finite set, you can definitely just count the elements, right? You have a finite set A, you just point to the elements one by one, 1, 2, 3, 4, 5, 6, 7, 10. So I can count all the elements in a finite set. But if you have a set that's equinumerous with n, then this means that you can write down a bijection. Let me actually write it this way, because we know it's symmetric. There's a bijection from n to a, and this bijection will give you a way to list the elements of a. Just list f0 first, then f1, then f2, then f3, right? In other words, you take 0 here and you map it over to f0. So these are elements in A, all of these. And since f is surjective, this list will eventually run through every possible element of A, because that's what it means for f to be surjective. So if you just list f0, f1, f2, f3, f4, f5, f6, etc., eventually you'll list every single element of A. That's really what a bijection, or that's one way to think about a bijection between n and another set is. It's a way to list the elements. So you know that z is countable because you can write z as, well, 0, 1, -1, 2, -2, 3, -3, ... It's clear that if I continue this list forever, I'll list every element of the integers. So that's why you would call a set in bijection with n countably infinite. Of course, if it's finite, it's still countable. So we reserve the word countable for either finite or countably infinite. And we say countably infinite when we want to make sure, when we want to be clear that it's an infinite set. Okay, so n is countable, it's countably infinite. Z is countably infinite. Let me also point out that right now, we don't know if there are even any sets that are uncountable. We don't know if there exist any uncountable sets at the moment. It seems kind of weird. How could there be an infinite set with so many elements that I could never list them all? So, but because we have the definition of countable and uncountable, this suggests that there will definitely be some uncountable sets. Those things will be infinite sets that you cannot put in bijection with n, which means that they're bigger infinities than n. So we'll see those in a little bit, but we're still in the countably infinite section. So let's see a first result. Theorem. Suppose that A is an infinite set. And you can list the elements of A in a sequence, right? A naught, A1, A2, dot, 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 such that every element of A appears exactly once in the sequence. Then A is equinumerous with n. Okay, again, like in order to do this, you need to sort of be able to give me a rule that will list every element of the set A, right? So like for Z, like I could write this as a sequence, right? So if I look at this sequence, 0, 1, -1, 2, -2, 3, -3, I can prove to you that every integer appears exactly once in the sequence. How can I do it? Well, right, so if this is A naught, A1, A2, A3, A4, A5, A6, how do I prove it to you? I say, okay, give me any integer you want, n, I will tell you exactly when it appears on the list, right? So if n is in Z, the point is, if n is negative, then A sub 2n equals n, right? All the negative numbers, A sub negative 2n equals n. If I want to get the negative number -3, then I can just take A sub 6. If I wanted to get the negative number -100, I can just take A sub 200. That'll get me there. And if n is, I guess if n is less than or equal to 0, that works. If n is positive, then I can just take A sub 2n minus 1. This will equal n. Right? If I want to get the positive number 3, I can take A sub 5. That's what the rule says. So I can prove to you that this sequence will list every possible integer. Okay. So if you can list all the elements of A in a sequence, then it means that you're equinumerous with n. Okay, so here's the proof. Let's suppose that A can be listed in a sequence like this: A naught, A1, A2, A3, etc. What do I need to do? I need to show you that A is equinumerous with n. That means I need to exhibit a bijection between A and n. So to show that A is equinumerous with n, we need to find a bijection f from n to A, or from A to n, but I think n to A is a bit easier. So let's define a function f from n to A by f of n equals A sub n. Right? So in other words, like f of 0 is A sub 0, f of 1 is A sub 1, f of 2 is A sub 2, etc. F of n is A sub n. Claim f is a bijection. How do I show that it's a bijection? I show that it's injective and surjective. So let's show that it's injective first. How do I show that something is injective? I suppose that f of n equals f of m. I need to show that n equals m. So suppose that f of n equals f of m for some natural numbers n and m. Well, what does that mean? To say that f of n equals f of m just means that an equals am. But what did we assume? We assumed that every element of A appears exactly once in the sequence. So since these two are the same element, they must be the same entry in the sequence as well. Since we assumed the sequence listed each element of A only once, this means that n equals m. Okay, why is it surjective? The point is that we assume that every element of A appears somewhere in the sequence. So for every x in A, by assumption, there exists an n in n such that x equals A sub n. X appears somewhere in the sequence because I assume that the sequence listed every element of A. Hence, for this n, f of n equals x, which shows that f hits every element of A. Okay, so really what this theorem is saying is that another way to think about bijections to n is just listing elements. A bijection from n to A is the same thing as a list of elements from A, where I've listed every element in A exactly once in this infinite list. So like the reason that I stated and proved this theorem is because this will give us sort of a nice, easy way to think about whether or not a set is countable. It's just, can I list all of the elements exactly once in a list of infinite length? But again, it's still not clear that if there are any sets that I cannot do this with, right? In fact, to me, if I were just very naively taking a guess, it seems like, oh, you could probably do this with every infinite set. Just list all the elements, right? Just list all of the rationals, just list all of the real numbers. Okay, so they all must be countable. The point is, though, that you need to be able to write down how you're going to list them in some way. So we still don't know of any uncountable sets. Right, so n is definitely countable. Z is definitely countable. I would say the next biggest set is Q. So what about the rationals? So that's my next question. Q question mark. Is Q countable? So in order to address this question, let me prove sort of a lemma, which is the following. The set n cross n is countably infinite. So if I take all ordered pairs of natural numbers, it seems like there's a ton of them. But it turns out that this is actually a set that has the same size as n. Again, I want you to think of this as kind of surprising. This set seems big. But it's equinumerous with n, even though it seems like there's way more ordered pairs, right? The picture is n, right? N looks like this. Right? 0, 1, 2, 3, 4, 5, 6, etc. This is what n looks like. I should do this in another color because it's not really part of my notes. It's just right? So n looks like that, but n cross n is huge. It looks like, right, there's dots here. Every ordered pair, you can think of it like as sitting inside of the Cartesian plane. right? So this is like 0, 0. This is like 0, 1, 0, 2. It goes up infinitely, right? 1, 0, 2, 0. It seems like there's way more dots in the bottom picture than in the top picture to me. But what this theorem says is that if I can find a way to list all of the elements of n cross n, then it will be countably infinite. So I'll just give you a proof sketch, just the idea. Proof sketch. So the idea is to organize n cross n in a way that we can list all the elements. Because the last theorem says that listing all of the elements is the same thing as a bijection from n to n cross n, right? Listing all elements is the same thing as bijection n to n cross n. This is by the previous result. So what I'll do is I'll write n cross n like a computer scientist would, which is really distasteful, but a computer scientist would call this point 0, 0, right? And then would call this point 0, probably 1, 0, but that. The point is I can write down the elements of n in a really organized way. And these go on. Here's all of n cross n. Now, if I said find a way to list all the elements of n cross n, what you could not do is you could not say, okay, well, first I'll list 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, etc. And then I'll list 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, because you'll never finish with the top row. There's no, and then I'll list 1, 0. So because you'll never finish the top row, if you try to do it like this, you will never list all the elements in this set. So we have to be a little bit cleverer than that. There is a way to list these, however. So what I'll do is I'll trace the following pattern. Okay, so I'll start at 0, 0. So I'll list 0, 0 first. Then I'll go to 0, 1. Then I'll go to 1, 0. Then I'll go to 2, 0, 1, 1, 0, 2. Then I'll go to 0, 3, 1, 2, 2, 1, 3, 0. Then I'll go to 4, 0, 3, 1, 2, 2, 1, 3, 0, 4. And I'll continue tracing out this pattern. The point is that this snake-like pattern now will hit every single element in this picture. So what is this function really doing? It's like the first thing you hit, here's all the pairs that sum to 0, right? The diagonals, I should say, this diagonal sums to 0. This diagonal sums to 1. This diagonal sums to 2. This diagonal sums to 3. So what this function is doing is, first I list all of the elements, all of the ordered pairs that sum to 0. There's only one of them. There's only finitely many of them ever. Then I'll list all of the ordered pairs that sum to 1. There's only 2 of those, so I can list those. Then I'll list all the ordered pairs that sum to 3. There's only 3 of those, so I can do that. Or 2, sorry, all the ones that sum to 2. There's only 3 of those, so I can do that. Then I'll list all the ordered pairs that sum to 3. There's only 4 of those, so I can list those. Then I'll list all the ones that sum to 4, 5, 6, 7, etc. And every single ordered pair has a finite sum. Therefore, I'll hit every single ordered pair. Right? Then you use this. I mean, I guess what I'm saying is you prove that every element is listed exactly once. The point is that once you know this pattern, you know that it's possible to do it, which means that it's in bijection with n. Okay. Why did I why did I prove this? Well, first of all, it's like kind of an interesting fact. Again, the bottom set seems a lot bigger than the top set. Second of all, fractions are almost like ordered pairs of numbers, right? Like the fraction 1/2, you can kind of think of as the ordered pair 1, 2. Now they're not ordered pairs of numbers because like 1/2 is the same thing as 2/4, and also you don't allow the ordered pair of 1, 0. You don't allow 1/0, and also I need to have negative numbers too. But in spirit, fractions are kind of like ordered pairs of numbers. So this is along the way to trying to prove that Q will actually be countable. Okay, that's my goal. I don't have that much time left to do it. Let me state a theorem and not prove it, which is an infinite set generalization of the pigeonhole principle. So let's call this a generalization of the pigeonhole principle. It's not the generalized pigeonhole principle, but it's a generalization of pigeonhole, which is if B is countable and F from A to B is an injection, then A is countable. Okay, so here I'm using countable to mean countable. It could be countably infinite, it could be finite. So if you ever inject into a countable set, you must be countable yourself. Okay, so I won't prove this. Proof is omitted. But hopefully, from an intuitive standpoint, it's believable. To have an injection from one set into another sort of means the domain is not any bigger than the codomain. So if B is countable, then A can't be any bigger. A must be countable, either finite or countably infinite. Okay, but I want to use this theorem that I improved to prove the following. The set of non-negative rationals Q greater than or equal to 0 is countably infinite. So I'm sort of sneaking up on Q here. Right? First I looked at n cross n. Now I'm going to look at non-negative rationals. So how do you show that a set is countably infinite? First you need to show that it's infinite. Then you need to show it's countable. Or first you show it's countable, then you show it's infinite. You need to show both. So first of all, I should say that we know that the non-negative rationals contain the naturals, right? At least as a subset. So Q is infinite, or Q greater than or equals is infinite, since you can find a copy of the naturals inside Q greater than or equals 0 just by taking n over 1 for each natural number. Right, and if you can contain a countable set, then you're, so if you contain an infinite set, then you're infinite. That's this thing. I guess I'll say we still have to prove it on the homework, but if you contain an infinite set, then you're infinite. Okay, so now I just need to prove that this is countable still. So let's define a function f from Q greater than or equal to 0 to n cross n. Well, as follows. So for each Q in Q greater than or equal to 0, let's write Q as m over n, where m and n are natural numbers. And the fraction is reduced, let's say. So I know that every single rational number can be written as the quotient of two integers, but since I'm looking at just non-negative rational numbers, I can choose both the numerator and the denominator to be non-negative. which means that I can choose them between natural numbers. Okay, so it's clear that every single non-negative rational number has one and only one representation this way. What I'm saying is just write it in lowest terms with a non-negative numerator and a non-negative denominator. Every q in q naught, so q greater than equals 0, has a unique representation like this. Right, then define f of q, which is f of m over n, to just be equal to m comma n, this ordered pair. Okay, notice that if I didn't tell you what m over n, what m and n were, then this function doesn't make sense. You can write a rational number as a fraction in infinitely many ways. What I'm saying is write it in lowest terms with non-negative numerator and denominator, then there's only one way to write it. So I'll map q to the numerator comma the denominator in this unique representation. Right, this map now is an injection because every different rational numbers have different reduced fractions. If you have the same reduced fraction, you have the same rational number. So this is an injection. And so now I have an injection from this set to this set. So by this theorem, if you have an injection from A to B and B is countable, then A is countable. So since n cross n is countable, we proof sketched that. By the previous theorem, q greater than equals 0 is countable. Okay. Now I have enough proved to prove the theorem that I wanted to prove. Let's call it corollary, actually, which is that the rationals is a countably infinite set. By the way, like I'm sort of jumping through a lot of hoops to get here. The point is that it's not that natural to write down a list of rational numbers that will list every single one once and only once. The problem is that lots of different fractions are actually the same rational number. So if I want to use this theorem and list every rational number once and only once, it would be really hairy. So rather than try to do that, try to come up with a really clever way of listing them, instead, I've sort of hidden all the work by just noting that n cross n is countable. And then I have an injection to n cross n from the positive rationals. So I don't need to cleverly list the positive rationals. I can sort of brute force it because I know that n cross n is countable. And now I can use that to show that the set of all rational number is countable. And the idea, it's really, I'll just give you a proof sketch. So the idea is to just alternate listing positive and negative rationals. Okay, so here's the deal. Since the non-negative rationals are countable, countably infinite, there exists a bijection f from n to q greater than equals 0. There is one. Okay, also, we may as well assume that f of 0 equals 0. Okay, if not, then f of something is equal to 0 because it's a bijection. So if f of 37 equals 0, then just swap 0 and 37. So define a new function. that swaps f of 0 and f of 37. So just wherever 0 appears on the list, just force it to the front. Make one swap. It's clear that you're still listing every single non-negative rational number. Okay, this is just a little bit of technical business. Let's just assume that f of 0 equals 0. Now what I'll do is I'll define a new function g from n to q as the following. So g of x will equal f of x over 2 if x is even, and f of x plus 1 over 2 negative if x is odd. So this function will do sort of what I want. Let me just show you. So right, what is g of 0? G of 0 is just f of 0, which is 0. Right? What is g of 1? G of 1 is negative f of 2 over 2, which is negative f of 1. Whatever f of 1 is. What is g of 2? 2, that's even, so you go by the first rule, that's f of 2 over 2, that's f of 1. G of 3 is negative f of 3 plus 1 over 2. That's negative f of 2. G of 4 is f of 2. What have I rigged up? I've rigged up a sequence that lists all, like, that alternates between negative and positive. So remember, this f was a function, was a bijection from n to q greater than or equal 0. So if you look at like f of 0, f of 1, f of 2, f of 3, sorry, that f of 2, let me list a couple more terms here. G of 5 is equal to negative f of 3. G of 6 is equal to f of 3. If you look at every other term, this list will exhaust the non-negative rational numbers. Right? First it lists 0, then you have some list of all the non-negative rationals. What are we missing? We're missing all of the negative rational numbers, but I've rigged it up so that every other term is negative of f of 1, negative f of 2, negative f of 3. These blue terms will go through all of the negative rational numbers. So eventually we'll list every non-negative rational number and we'll list its negative. And since we'll have listed every single rational number, this will give us you can use this to cook up a bijection, right? Then you show that G is a bijection. It follows from the fact that F is a bijection and that every rational number is either 0 or positive or negative, right? The negative of a positive one. Again, the point is that listing all of the rational numbers is kind of tricky. So I've had to do some voodoo where first I showed that n cross n was countable. I used that and a little trick to show that the non-negative rationals were countable. And then you can sort of alternate between the negatives and the positives to show that the set of all the rationals is countable. But the point is that you can actually show that Q is a countably infinite set. So our next biggest set that we tried actually is still countable. So we still don't know the existence of any uncountable sets. But next time, we'll see a really famous and very beautiful theorem that the set of real numbers is uncountable. So there are infinities bigger than LF naught. There are infinities bigger than the size of the natural numbers. But you need to go all the way up to the real numbers to get there. The integers and the rationals are both countable. They're both in bijection with n. Okay, so there was a lot of stuff today. I think this stuff is pretty cool. I hope you do too. But it's pretty tricky. So you'll have a homework assignment where you prove some of these things and hopefully get a little bit more used to working with countably infinite sets. And then next time we'll talk about uncountably infinite sets. All right.